Hi guys, welcome to my channel. In this video, let me explain the regular expression to epsilon NFA, epsilon NFA to DFA, and DFA minimization. Let us go in detail with the slides and let us understand. The agenda of today's presentation, regular expression, Thompson's construction, example, epsilon NFA to DFA, subset construction, DFA minimization, advantages and application. And finally, we'll end up with the summary. Let us go in detail with the slides. A regular expression. The definition is to specify a set of string. It is nothing but to describe the patterns of the string. In the compiler design, the regular expression mainly used to specify the structure of the tokens in the source program. In my previous videos, you can see the regular expression in depth. So some of the operators are concatenation, union, clean star. Examples are like this: a comma ab with respect to the concatenation, union operator using a by b, clean star abb. A regular expression, you can see the small diagram here. Let us move to the next slide. Thompson's construction. Purpose of this is to convert the regular expression into an equivalent epsilon non-deterministic finite automata. You can see the construction rules. Regular expression after applying the Thompson's rules, and it is used to convert into the epsilon non-deterministic finite automata. Some standard rules are symbol. So A is the regular expression which is given to the non-deterministic finite, which is represented as like this: Q0 A Q1. Q1 is the final state, Q0 is a start state. I hope you guys understood. Let's move on to the next slide. Union. Union, to add a new start or end with epsilon branches. You can see here the diagram and you can understand in detail. So here A epsilon Q0. This is the new start. Concatenation operator joins the two non-deterministic finite automata with epsilon. So you can see Q0 A transition to Q1, epsilon transition from Q1 to Q2, B transition from Q2 to Q3. I hope you guys understood. Clean star adds a epsilon loop for 0 or more repetition. You can see here A union B clean star ABB. You can use the n number of epsilons in this expression. Uses the E transitions to connect the different fragments. I hope you guys understood. Let's move on to the next slide and let's understand in detail. Worked example. For this expression, these are the following steps. First, build the NFAs for A and B. Then we are applying the union. Then we are applying the clean star. Then concatenating A. Then concatenating B. Then concatenating B again. And next we are generating the epsilon non-deterministic finite automata. This is how working will be done. Let's move on to the next slide. The advantages of Thompson's construction. Easy recursive algorithm. Uses the epsilon transitions. Simple implementation used in the lexical analyzer to generate the token and to identify the patterns. Epsilon non-deterministic finite automata to DFA deterministic finite automata. Some of the standard construction steps are: compute the e-closure, that is start, find the moves, compute the e-closure of the result, repeat until no new state. I hope you guys understood. Let's see in detail in the further slides. So e-closure 0. You can see the right hand side one diagram. E-closure Q naught transition epsilon 2 to Q1, Q1 transition A to Q2, Q2 transition B to Q3. This is the epsilon non-deterministic finite automata, which is converted into the deterministic finite automata. You can see the table, transition table. A to small a transition to B. It is there. From B to small a transition is no, we don't have any transition. For B, small b transition to the C we have. For C, we don't have any transition, so it is a dead. I hope you guys understood. Let's move on to the next slide. Advantages of DFA. No epsilon transition. So because no epsilon, it is the faster execution. One active state is there. Easy implementation is there. These are the advantages. Let's move on to the next slide. DFA minimization. The main agenda or goal is to reduce the states without changing the language, which removes the unreachable states and partitions of the final and non-final states. It's very clearly partition has been made, defines the partition and merge the equivalent states. Let's go in detail with an example, we'll understand. The goal is to reduce the number of states in the DFA without changing the language accepted. Each language has its own set of rules, so we don't need to change the basic or predefined language. The given DFA was ABCD states. Alphabets are 0, 1. Start state is A, final state is D. Let us go in detail and let us understand. This is the transition table. A, B, C and D are the two final state. We are constructing this table, dividing the stages into two groups. Finally, separate the final and non-final states. Group 1 is a final states, that is CD. Group 2 is a non-final state, that is AB. Step 2. Check the equivalent states. Compare the CD. For C to C, we have the input 0. C to D, we have the 1. D to C, 0. D to 1 is both always moves to the final state. So C equals D, which is the equivalent state, because in both the state pairs, which has the 2 also, C also it has, D also it has. So they are equivalent, so they can be merged. Both states has both the transition to each states. So it is equivalent. Compare A and B. B is a non-final state. Again, A is a non-final state. For B, it is a C is a final state and A is so 0. A goes to B. B goes to C. C is a final. Different behavior, so it is not equivalent. So A is not equal to B. So we are not merging. I hope you guys understood. Let us see. Merge equivalent states, merges the A and it has the transition to the final states itself, not non-final states. So we are merging. This is how it is. Again for this is the diagram. A to B 0, B to A 1, A to CD to A is 1, from A to CD is 0, for self is 0 and 1, CD self. I hope you guys understood. Original DFA states are 4, A, B, C, D. Minimized DFA states are 3, A, B, C, D is the one state. DFA minimization removes the equivalent states and produces the smallest possible DFA. I hope you guys understood. Let's move on to the next slide. Advantages and applications. Advantages: efficient lexical analysis, reduces the memory, faster matching. Application: in the compiler we are using this regular expression, DFA, NFA, finite automata, and regex engines we are using. Pattern matching, we are using this regular expression and finite automata. Comparison table, you can see futures, Thompson's construction, epsilon NFA to DFA, DFA minimization. Inputs are regular expression, epsilon NFA and DFA. Output, epsilon NFA for Thompson construction, DFA for epsilon NFA to DFA, minimal DFA for DFA minimization. Goal: construct the epsilon NFA, removes the non-deterministic and reduces the state. Epsilon transition: yes, Thompson's construction has a epsilon transition. Epsilon NFA to DFA, removed epsilon transition. DFA minimization, no epsilon transition. Deterministics: no for Thompson's construction, yes for epsilon non-deterministic finite automata to deterministic finite automata, yes for deterministic minimization. I hope you guys understood. Let's move on to the next slide. Summary: the pipeline, regular expression which is given to the epsilon NFA, from that DFA, from that we are giving to the minimal DFA. This process is used in the compiler lexical analyzers. I hope you guys understood. Thank you. If you have any doubts, any queries, please write in the comment box so that I can respond. Thank you.